afternoon. So Professor Adjih made a mention of fountain codes for massive IoT. He said that there are some potential benefits at the cost of computational complexity. So that's something I'm going to actually talk about a little bit more in depth. So it's a serendipity that he happened to mention this topic. It was not planned before. In any case, so the topic I'm going to discuss is that of reliably broadcasting files in massive IoT networks, massive machine-type communication networks, with the help of rateless codes and also with the help of device-to-device cooperation, which rateless codes will help us implement. So in this context, I am talking about mMTC in the general sense, because if you look at the subtitle of this talk, it is a case study on over-the-air firmware updates over LoRaWANs, which are not 3GPP standard. But so basically, I'm talking about mMTC in the general sense, where we have a bunch of sensors, actuators, and devices like this, which are communicating wirelessly. Potentially, there's a large number of devices. So typical example we have in mind are maybe monitoring applications, where a large number of sensors are transmitting their data to a gateway. So in these networks, the primary KPIs usually are energy efficiency, because sensors need to last a long time. Protocols that we design for these networks should be simple, not a lot of inter-device coordination, synchronization should be needed. They should be scalable, of course, because we have to be able to incorporate a large number of sensors. But in addition to these KPIs, do we need reliability? So in this case, we are not talking about URLLC. So for a general mMTC network, typically on the uplink, sensor to gateway, reliability is not a very stringent concern. Some amount of packet losses are generally tolerated. That is the typical perspective for mMTC, and that's what brings mMTC apart from URLLC. In any case, if a sensor needs to reliably deliver one packet for some reason, maybe it's an urgent data, very important data, then some form of retransmission-based mechanism like ARQ can be used. It also has some caveats, but in general, it is doable. But there are some cases on the downlink, from the sensor to the gateways, where we do need reliability. One very common typical example is that of updating sensor firmware. So in response to security threats that have newly emerged, we might need to update the firmware of all the sensors that are there in a network. That would definitely require reliable broadcast. Now in this case, retransmission-based mechanism like ARQ will not work well because they don't scale. I have to transmit a large number of packets which constitute the firmware. For each packet, each sensor has to send back an acknowledgement. If all of them transmit at the same time, they're all going to collide, nothing will be available. So we'll have to have a very complex scheduling mechanism so that everybody gets to transmit the acknowledgement for every packet, but without colliding. That's going to be pretty difficult. The other obvious problem with that approach is the amount of energy consumption, because if a sensor has to transmit that many acknowledgements, it's going to run out of its battery pretty quickly. So in that case, to circumvent these problems, one potential technique is that of rateless coding, of which fountain codes, as Professor Adjih mentioned, are a part of. So in general, the basic principle of rateless coding is to work with these source packets. So let's suppose these are the packets constituting the firmware upgrade, for example. So in a normal scenario, I'm going to transmit these source packets or information packets one by one and wait for an acknowledgement. With rateless coding, what can be done is we can transmit random linear combinations of those source packets. Each source packet multiplied by some random coefficient chosen from an appropriate finite field. Add all of them up to generate a random linear combination that constitutes a coded packet. It's an application layer coded packet. That coded packet is then channel encoded, modulated, transmitted as usual. So this channel encoding, the underlying assumption is that this encoding has transformed the channel from a channel with errors to a packet erasure channel. So what I have at the receiver is a bunch of coded packets. These coded packets represent linear combination of information packets, and the receiver can solve a system of linear equations at some point to retrieve all these D1 through Dk, all the information packets, and then reconstruct the entire file. So that is the idea. So for this CJ, for the coded packet, all these coefficients A1j, A2j up to AKJ, this is known as the encoding vector. So it's very important in found encoding or in rateless coding systems that when I transmit a coded packet, along with it, I somehow convey the encoding vector as well. And then and only then the receiver will be able to reconstruct the information packets. Now, including that encoding vector in each packet, again, will take up a lot of energy because encoding vectors can be long, depending on what is the value of k. So for that, what is normally done is to exploit the fact that these numbers are being generated with the help of some pseudo-random number generator. Depending on what the seed of the pseudo-random number generator is and what is the sequence number of the packet, we can map the coded packet sequence number to the particular encoding vector. So the receiver, by knowing the sequence number of the coded packet, it can reconstruct with accuracy the encoding vector. So that way we don't have to actually tag on this entire thing to each coded packet. That saves some energy. In any case, however we choose to convey the encoding vector, the end result is that the receiver is supposed to solve a system of linear equation by whatever method is available. Most obvious is Gaussian elimination. That is computationally too expensive. So there are simpler methods available, and the way the decoding is done and the way these coefficients are generated, the probability distribution on these coefficients, these two together define what type of rateless code we are dealing with. So for example, there are fountain codes. Within fountain codes, there are Raptor codes, LT codes. So each of them have their own degree distribution, so to speak, and decoding methods, notably belief propagation or belief propagation enhanced by some other means. So I'm not going to talk about all that, but basic idea is this. Now, if we have a rateless code, what benefit can we achieve? So first benefit, of course, is that we don't need to have the acknowledgement transmissions. Only one acknowledgement per file, so to speak, the firmware upgrade or whatever it is. Only one acknowledgement should be sent by the receiver once it has reconstructed all the information packets. So that way, far fewer number of acknowledgement transmission. But and that way, the scalability problem is more or less overcome. But can we get any other benefits out of rateless coding? Yes, the answer is yes. And for a long time, people have worked on enabling cooperative communication by exploiting the properties of rateless codes. So that concept can be extended to using rateless coding along with device-to-device communications so that we can expedite the transfer of information. So here's an example of that. Let's suppose there's a source that wants to transmit or deliver one file to both destinations D1 and D2. D1 is nearby, D2 is farther away from the source. So most likely D2 will have a lot of packet erasures, D1 will have fewer of them. So if I have to transfer the file without fountain coding, what I'll need to do is I will have to transmit each of the information packets, wait for an acknowledgement from both the receivers. Once it gets both acknowledgement, then it moves on to the next packet and so on. If I do fountain coding or rateless coding, S can start transmitting rateless coded packets without waiting for any acknowledgement. And let's suppose that D1 is able to decode the file first. It gets exactly as many linear independent combinations of the source packets as there are source packets themselves. So once they get it, once D1 gets that, D1 is able to reconstruct the file. At that point, D1 can tell S to stop and then start making its own, running its own fountain encoder from the point where S had left off. By the phrase where S had left off, I mean it can start fountain coding or rateless coding from the sequence number at which S stopped. Because of that one-to-one mapping between the sequence number of a coded packet and the state of the pseudo-random number generator and the encoding vector. So that way, D1 can continue the fountain coding process, so to speak. So this way, what will happen is that because this D1 to D2 link is stronger, D2 will start receiving packets over a better link, fewer erasures, quicker update delivery, quicker file delivery. So that way we can expedite the broadcast process by involving D1 in a device-to-device communication setup. Now the question is, this simplistic idealized example, can it be translated to a large mMTC network where there are many devices? Hardly any coordination. The devices don't talk to each other. Can we still do it? In this work, so what we have been trying to figure out is there any benefit, or is there first of all a way to incorporate device-to-device communication to a rateless coding setting? And if it is there any benefit? So for that, we looked at the question of firmware upgrade delivery in LoRaWANs. And we tried to design a very, very simple bare-bone channel access protocol involving D2D communication. And we saw that there is substantial improvement in theory, at least, which have to be refined in the future, but I want to talk about that. So just to give a background on what we mean by, or to give a background on the problem of firmware update over there in LoRaWAN. So this thing is shortened to FUOTA, F-U-O-T-A, and there's a FUOTA working group for LoRaWAN, and they specify typically the guidelines for carrying out the FUOTA process. So basic idea is simple. We have a gateway. There are a bunch of sensors who need the upgrade. Those sensors are formed into a multicast group. Each of these devices then is asked to operate in class B or C LoRaWAN. So just to give a background on that for those who are not familiar, LoRaWAN devices can operate in three modes: class A, class B, class C. Class A devices, they listen on the downlink only following a transmission. For a short time, after each transmission, they'll open the receive window and then go to sleep again. That does not work that well for firmware delivery, update delivery, because they have to be in the listening mode for a long, long time, even though they don't have anything to transmit to the sensor, to the gateway, sorry. So they move to some other class, either B or C. In class B, there are some synchronizing beacons from the gateway. With that, the sensors are synchronized. They periodically open their receive windows. During those receive windows, the gateway can transmit. Or they can be moved to class C, in which the sensors are always in the receive mode. That is extremely energy inefficient, so generally class B is preferred. But again, the general idea that actually concerns us is the thing that for FUOTA, the devices have to be in receive mode even though they don't have anything to transmit themselves. And of course, because we have synchronizing beacons, we can incorporate some time slotting. In this case, the general LoRaWAN does not have the concept of time slotting, but during the FUOTA process, when it is going on, we can do that. Then the firmware update is divided into fragments. Each fragment is put in a LoRaWAN packet or a link layer frame, so to speak, and those frames are broadcast. So the working group suggests using application layer coding to correct for frame erasures. So in their standard, they have proposed a suggestion, not a requirement, but a suggestion to use an application layer LDPC encoding procedure. So all the information packets or the source packets or the source fragments in this case, they are encoded using an LDPC encoding matrix of some fixed rate, and those LDPC encoded application packets are transmitted using the LoRa protocol, LoRa communication technology. And as usual, the receiver can decode that LDPC code and find out what the original source fragments are. Now, in the research community, however, very recently, there was a proposal saying that rather than using the fixed rate LDPC code, it is better to use a rateless code for reliability purposes. Despite rateless code's higher computational complexity, the benefit is that if I have a fixed rate LDPC code, once I run out of all the redundancy, the far enough devices may or may not be able to decode the entire upgrade. Most of the times, there are some devices which are very, very disadvantaged, very far away. They get a lot of erasures. So such devices will need an LDPC code of a very, very low rate. Now, whether such an LDPC code is available, that's one question. Of course, there can be other rate compatible LDPC codes sort of approach that has not been explored yet, but that obviously is a possibility. But the other possibility is to use a rateless code. So we take the firmware fragments and broadcast coded fragments just using that procedure of random linear combination. Same procedure. Then the devices continue collecting the fragments. Once they are able to decode the code, they're going to send an ACK. So once all the devices have sent acknowledgements, then the or once all the gateway has received acknowledgement from all devices, it will stop transmitting. Now, can we integrate device-to-device communications into that framework? So one idea is that since the devices are transmitting acknowledgements anyway, why not tack on one coded fragment into each acknowledgement? If we do that, and assuming it's an omnidirectional antenna, whatever the devices are transmitting, some amount of energy will reach their nearby devices as well. So they can then try to receive them, and then that will contribute to faster delivery of the update. And that is very important in this case because there are very strict duty cycle restrictions on LoRa transmissions because of their operation in the ISM band. In the European Union, it's 1%, which means that once the gateway transmits something, it has to wait for a very long time before it can transmit something else. So during this silent period, these acknowledgements will be transmitted. So these acknowledgements have no fear of interfering with the gateway's transmission, although they have a fear of interfering among themselves that we will tackle later. But in any case, there are sufficient amount of vacant slots in which the devices can send their own coded fragments in the hope that somebody else will receive them, and then their decoding will be faster, sped up. So there are many questions here. So one question is a single acknowledgement per device sufficient? If there are very few devices, probably not. If there are many devices, then maybe even one might be too much, in the sense that there will be a lot of collision if many devices send at the same time. Then the other bigger problem is how to ensure that the other devices are listening for the acknowledgement. Because in a regular FIOTA setting, the devices know exactly when the gateway is going to transmit, and for that time they are going to open the receive windows. Now these acknowledgements will also come. We don't know when they will come. Unless we have some sort of a synchronization mechanism, how do the devices know when to look for acknowledgement from other neighbors? That's one question. And the third is, how do I generate the coded fragments for the acknowledgement? Because these coded fragments, that will be put into the acknowledgement packets, they should be such that they are not duplicates of some coded fragments that the sensor, that the gateway or other sensors have already produced. So these are the questions. So let us tackle them. So let us first try to formalize the transmission procedure. So at the link layer, this is what we do. Every TG slot, the gateway transmits it coded fragment. From TG to TG, there are these vacant slots. Within these vacant slots, we reserve some of the slots immediately following the gateway transmission slot for acknowledgement transmissions. So these are the slots in which devices can transmit their acknowledgement. So this is what we call the acknowledgement window. Now once a device receives a complete update, it transmits NA number of X, NA being a variable that will have to be a system parameter. So we are not looking at only one acknowledgement as such. We are keeping that a tunable parameter. And each acknowledgement will be sent in a separate window, which means that if suppose a device gets its complete update during this gateway transmission, it's gonna transmit its acknowledgement, NA acknowledgement. One will be transmitted within this window, the other one will be transmitted within this window, and so on. So in a single window, they're not going to transmit more than one acknowledgement. Then how do I find the slots within which that acknowledgement will be sent? That will be picked up at random. So it's basically just to reduce the probability of collision, it is this random back-off mechanism we have implemented. And for all the unfinished devices, they will be in the receive mode during this entire time, from starting of the gateway transmission slot to the end of the acknowledgement window, corresponding acknowledgement window. So the extra price we are paying in terms of energy spent for listening is this extra time. Normally they will be listening this, now they are listening the entire duration. So that's one point regarding transmission. Now generating coded fragments of the devices. As I said, we want to ensure that devices are not generating duplicate coded fragments. Again, it is not possible to ensure because we don't have any, there is no central coordination. It is not feasible to keep track of which device generated which coded fragment. So again, we take a random approach. So what we do is, any device, when it has to transmit an acknowledgement, it picks a random sequence number for the coded fragment that is chosen from the pool of all sequence numbers, starting from the last sequence number the gateway used and the maximum possible sequence number. So the maximum possible sequence number generally is, there's a field for the sequence numbers. Usually it's a 16-bit or 32-bit field. For example, the 3GPP Raptor code, if I'm not wrong, it has a 16-bit sequence number. So 2 to the power 16 minus 1 would be the largest sequence number. So whatever is the sequence number the gateway used at last, 2 to the power 16 minus 1. That's the entire window over which one random sequence number will be used. And obviously that will reduce the amount of collision to the best possible extent. Now, what about the link layer parameter, file layer and link layer parameters? So at the file layer, we have to look at two things. One is the frequency band. So in a typical LoRaWAN, there are multiple frequency bands available for transmission. The gateway will generally use a fixed frequency band. Or there might be some sort of a known hopping pattern if we know that there is some specific partial band jamming or whatever. So that we have kept open. But in general, it is expected that a fixed frequency band, the same frequency band, will be used for all transmissions. And what about the spreading factor? The LoRaWAN being a chirp spread spectrum modulation, it has to specify the spreading factor of each transmission. The spreading factor determines how robust the transmitted signal is to channel noise and interference as well. So generally there are 6 spreading factors available in commercial LoRa devices, 7, 8, 9, 10, 11, 12. If I use a small spreading factor, packets will be shorter, so energy expenditure will be less, both for transmitting and for receiving. But then the coverage will also be less because the receiver sensitivity, the absolute value will be higher. But then if I go for a large spreading factor, I can cover longer distances, but the energy expenditure, transmission time, all these things will be higher. In general, the conventional approach is to use the largest spreading factor that can cover all the way up to the network's edge. That way, the problem is that the nearby devices have to receive over a spreading factor that is far too long for their own needs. They could have used the smaller spreading factors, spend much less amount of energy and time receiving. So can we do better? So what we propose is that let us employ a set of spreading factors, not just one spreading factor. Start from some small spreading factor and then keep increasing the spreading factor over a period of time. So let us send the first k prime frames using the lowest spreading factor, then make the spreading factor 1 higher for the next k prime frames, and so on until we reach the highest spreading factor, whatever highest spreading factor we have defined here. At that point, from that point onwards, all new transmissions will use the exact same spreading factor, the highest one. So a common example, that we have used in our simulations is k prime is k. That means k prime is the number of packets that constitute the file. Then L is 7, M is 12. So entire gamut of spreading factors. But this is not always the optimal choice. I will show later. And for the acknowledgements, for the transmissions by the devices, we're going to use the same frequency band and spreading factor as employed by the gateway. Why? It's because when a device is trying to receive this device-to-device communication, the D2D packets, it needs to open its receive window over a certain frequency band and over a certain spreading factor. They may not have multiple demodulation paths. So the SF and the frequency band both have to be fixed. How do the devices know which one to use? By knowing that whatever spreading factor and frequency band the gateway used for the last transmission, the same is going to be used for the D2D transmission as well. So that is the general framework. One potential downside of that approach is that a device has to listen for the acknowledgements over the entire acknowledgement window, all those orange colored blocks. We can do a little better if somehow the gateway knows which slots will be used for D2D transmissions. So how can we try to implement something like that? So we call that X slot notification. So if we want to have X slot notification, the first acknowledgement that a device sends does not carry any coded fragment. Instead, it carries the choice of the time slots that the device is going to use for its future acknowledgement transmissions, the remaining NA-1 acknowledgement transmissions. Then, in the next packet that the gateway is going to send on the downlink, it is going to include that information. It's going to include the slots within the next ACK window that are going to be used by different sensors for their own D2D transmissions. So that way, the other sensors who are not finished yet, they know when to open their receive window. So these are the two ideas. So we did a performance evaluation over a very standard setting. We have uniformly distributed devices over a circle around the gateway. There's Rayleigh fading on the links and pause-on-point process distribution on the interference. Fairly standard. We are trying to transmit a 10 KB file. Number of devices, 50, 100, and 200. Actually, we went to 400. I should have included that. Fragment size 50 bytes. Number of fragments 200, and so on. Duty cycle 1%. So these are basically representative numbers. The conclusions remain the same even if we change them. But before looking at the rateless coded transfers performance, let us look at this figure just to check how it works when we have a fixed rate encoding, no rateless codes. So we fix the rate of the code, the amount of redundancy that is transmitted is fixed. And for ease of simulation, we assume that the fixed rate code is an MDS code. The moment we have K coded fragments, we are able to reconstruct the entire thing. So if we do that, as we see, if we have a network radius of 100 meters, the percentage of devices that are updated is this blue curve. And that obviously depends on the code rate, because if you have a very small code rate, we are transmitting a lot of coded fragments, so there's more chance that many devices get a lot of fragments in order to be able to reconstruct the entire file or entire update. If we make the network radius larger, as intuitively expected, the percentage of devices updated will come down, because the farther away devices, they do not have such a good link. So for the same amount of redundancy, fewer percentage of nodes are actually able to reconstruct the update. So the point to take away from here is that if we are using a fixed rate code, first of all, we are going to need a very, very slow code rate if our network is this large. That's point number one. So one remedy for that is to simply make the network smaller, have many gateways, each gateway covering only a small radius. That is obviously a solution. But if we don't have that, if we want to do with a single gateway, this is what is going to happen. So we have to have a very low rate code. More importantly, that fixed rate code's rate depends on various network parameters. Here it is shown only for the network radius, but it will also depend on the interferer density. It will also depend on transmit power and all these things. So we have to have a very, very good estimate of what the fixed rate should be if we want to take this approach. By contrast, if we go for rateless coding, these issues are not there. We can simply continue transmitting as long as we want. So reliability wise, rateless coding will definitely help. That is that's not a question, that is subtle. Now, with assuming that we have a rateless code, what can we gain by doing all these additional enhancements? One is we do this SF rotation, multiple SFs, multiple spreading factors, and we have device-to-device communications. And it turns out that the improvements are pretty large. Here we are comparing the update time. By update time, it is shown for a device on the edge. So the farthest device from the gateway, how long does it take for it to get the complete update? So that update time here is shown for the case in which both the schemes are actually using the same spreading factor 12, spreading factor 12. This guy has device-to-device communication, the orange one or the red one. The blue one does not have. So this gap is because of the device-to-device communication. So much lower update time for the RC D2D protocol compared to simple RC with a fixed spreading factor. Now that gap actually increases as we move on to other SF sets. So this one means that this blue line is using a single spreading factor, that is spreading factor 11. There is no D2D communication. This one uses a set of spreading factors 11 and 12, and there is D2D communications. So this is what we get in this case. Then here the tall blue line is using fixed spreading factor 10, no D2D communication. This one has spreading factors 10, 11, 12 and D2D communications. Over here there is no blue line because we could not complete our simulation with the rateless code with a fixed spreading factor. This spreading factor 9 is too small to actually reach all the devices. So no matter how many iterations we run, simulation just doesn't converge. It did not end after running it for many probably more than a day. It did not converge. On the other hand, not converge means it did not compute. Whereas with with D2D communication and spreading factor rotation, that problem is not there, because even if we started with a very small spreading factor 9, eventually we will move down to spreading factor 10, then to 11, then to 12. So at the end of the day, all the spreading factors were used, and that contributed to the completion of the update. And on top of that, we had the device-to-device part, expediting the overall update. Then here is a rough estimate of the energy consumption, how much energy these two protocols are consuming. We can see that if I am using only spreading factor 12 for both cases, one with only RC, the other one is RC plus D2D, there's slightly less energy consumption for RC D2D. So which seems counterproductive, because in D2D communication, the devices are spending extra energy by listening for incoming frames. But however, the point is that this one is getting over a lot earlier. So even though they are spending extra energy waiting for D2D packets, but overall number of slots they are waiting is actually less than over here, because in this one, without any D2D, a lot of packets have come in which eventually failed, which resulted in erasures. So energy is being consumed in those erased packets as well. Here there are fewer erasures, because many of those packets, D2D packets, are coming from their neighbors, which are correctly received. So there's still some energy consumption benefit. In this case, however, there's a slightly higher energy for D2D than simple rateless coding. Here is the opposite. So it's hard to tell without simulating this which one will take more energy and which one will take less. But in general, they are either comparable or less than simple rateless coding without D2D. Then, of course, all of these things will depend on many network parameters. So one of the things is how many devices there are. If there are a lot of devices, we'll expect that more D2D communications will happen. So faster update. But if there are too many devices, then again there might be a problem where a lot of collisions happen. So in these things that we examined, what we see is that as long as we have, up to a number of devices equal to 400, the overall update time, the latency, has actually decreased from 16.5 to 2.0 hours. And it is expected that if I make it very, very large, then at some point maybe performance will saturate or even go down because of the excessive pollutions among D2D frames. So that one proper protocol has to be developed in order to tackle that issue. And here we show what is the optimal spreading factor set. So we talked about using a set of bunch of spreading factors, L, L plus 1 all the way to M. So what are those L and M? So if I have a very few number of devices, 50 devices, it's not necessarily an mMTC network, but there are multiple devices but rather small, it's better to use only spreading factor 12, because we want a spreading factor that goes large enough. Otherwise, what might happen is that there might be some devices at the edge which are neither well connected to the gateway nor well connected to any other neighboring device, and neighboring devices will transmit only a limited number of packets that is not sufficient to complete the decoding in those at those nodes. Then as we move higher and higher in the node density, it is better to actually go for larger spreading factor sets. That's an observation we have made. And then if I have the X slot notification, so whatever I showed so far, they do not have the X slot notification, the one in which devices tell the gateway beforehand which slots they are going to use in the future transmissions. If we incorporate that, what happens? First of all, energy consumption comes down. Expected, because devices are now not waiting entire ACK window listening. They are opening their receive windows only when needed. There will be many ACK windows where no D2D communications is expected. So they'll be completely silent, completely idle. They'll not receive at all. So energy consumption comes down. Update time goes up a little bit. The reason is that now we have to rely on the gateway to communicate the correct X slot information to all the devices who are then supposed to open the receive windows. Sometimes the first acknowledgement packet from the intended transmitter of the D2D packet may not actually reach the gateway. In that case, the gateway cannot tell the other devices to wake up accordingly. That is one issue. And sometimes the gateway's transmission may not reach the devices, who then don't know when to wake up, when to open the receive window. So some amount of increase in the update time is there, but energy consumption comes down. So all this initial work shows that yes, in terms of latency reduction of firmware updates and reliability and ensuring reliability, fountain codes or rateless codes indeed have the potential to accomplish what we want. Issue, of course, is computational complexity. That needs to be tackled, how we can best handle that. Of course, there are these linear time encoding and decoding methods for Raptor codes are available. So that is one ray of hope. In addition, if needed, we can actually divide the overall firmware update into smaller blocks. Rather than running the fountain code over 200 blocks, maybe we can divide them into smaller 45 blocks of 40 size, and then we run it. So that way, some amount of complexity might be able to reduce some complexity. It is possible to come up possibly more intelligent ways. That needs to be seen. And we showed it for the broadcast scenario, but unicast can also benefit. If there is a multi-hop unicast problem, then similar things can be used if we have a cooperative relaying scenario, multiple D2D devices willing to forward some data. Although that needs to be seen, but potential is there. Other issues like transmission parameter selection. In this case, we talked about the frequency band as well as the spreading factor. But if we go for some other standard, the phi and link layer parameters might be different, because this LoRa one is a motivating scenario. This is something we used because it's an open problem, and people have been working on this faster update delivery. That's why we worked on this. But if we look at some other next generation mMTC network, other types of phi and link layer may need to be handled. Then the scheduling is what we showed here are extremely basic forms of scheduling. One is just randomly transmit over NA time slots. The other one is take help of gateway. It's possible. Likely we can come up with something better. That is one open issue. The third issue, which is beyond my grasp, is the issue of security. Anytime we have D2D communication, security issues come up. We are letting someone transmit packets to firmware parts of the firmware to the other devices. So security issues might be there. That also needs to be seen. Okay, so this is what I wanted to talk about. So thank you. I'm open to questions.
Long live India and France friendship.